Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about computed tomography scans or CT scans. So let's dive deep into it. So what exactly is the problem that we need to compute something? Well, the problem is that doctor wants to see inside your body and ideally without cutting you open. For example, if a doctor wants to know that I have slip disc, it should not require, let me slice it open and see. That should not be the case. So that's the whole point. Now, like, can't we do X-ray? Well, it can work and it is really good for hard objects, aka your bones. It's really useless for soft tissues and it is not 3D. While whenever you see X-ray images, specifically if you are seeing the side and front profile, it gives you an illusion that it's 3D. It's not. Mathematically, this is compressed data point, meaning from the axis of photon emission, basically light is coming here, I'm getting a chest X-ray like this, the data is compressed here. Basically, you do not know which bone is where. Of course, there will be some shadow characteristics and psychologically, the bone's supposed to go like this. So that creates a scenario where it's like, this is good for bones. Anything else is like, lol. You can have some idea. Like, again, doctors can use this to make useful thing, but again, a majority of the crunching is being done by their brain, not in this. The data is not here. It's not 3D, it's 2D. So that creates an issue. And 2D shadow data, basically these things are really great for bones. This is how the very earliest X-rays used to be. And again, even in that time, you could easily see things. And then we started to go into much higher resolution. But when it comes to tissues, lol. Basically, if you want to see cancers or blood clots, God help you. So we want something that is easier. Now, is this better or MRI? MRI is harmless, but it's psychologically destructive. As in, like, I have no idea how the heck people can get through MRI very comfortably. I'm like, I have no idea how I had endured it. It's A, too cramped. B, I cannot move. C, it's loud. What the hell? And again, cat, 2-3 minutes, boom, go home, done. And again, it's not like, oh, you cannot have metal this and all that. Oh, that's also not there, because okay, many implants are metallic. So fundamentally, this is a good tool, but does come with a consequence of radiation. So there is certain problems. So how can we see inside human body without any issues? Well, first you have to understand the mathematical problem, because if you show anyone this sort of side profile and front profile, and you give this to an artist can give you a very almost accurate looking, realistic looking skull. And again, I used to do that. That was our job. Like, we did not used to get an X-ray of the car. We are just like, okay, this is the car, front view, side view, we used to model it. So because you can't get mathematics done from it. Why can't you get mathematics done from it? Because data is not there. You have compressed the slice. Meaning, if you look into a 3D coordinate system and you want to create what we call voxels, basically volumetric pixel, in those sort of scenario, this is 2D pixel, and you have like this, and you're like, okay, let me cross-reference them. Yeah, that creates what we call impossible problem to solve. Meaning, XY coordinate will make voxels. That's awesome. But if you try to solve it mathematically, oh, I have one projection, another projection, let me calculate it. It becomes what we call infinite solution problem. The easiest example for this, imagine this as one slice. Imagine multiple of this slice, exactly how you have 3D printer slicers. So if you have lots of slice, tada, 3D object, same thing with this. But again, you have to solve this. Can you solve this? Short answer, no. Physics does not allow you to solve it. Why? Even though from here to here, it's a fixed value. Let's just say 45 or 41, whatever have you. And you are supposed to get that exact value in all of them, in X coordinate and Y coordinate. Then what's the problem? Well, there is billions of ways of getting that. For example, how can you get a number 5? Well, 1 plus 4, 5. 5 plus 0, 5. 3 plus 2, 5. Now imagine doing something like that in this. It would be odd infinitum compute. Now you could try to paint it, but at that point you are not seeing what's happening inside the body. You are projecting what you want to see inside the body. So that's why we cannot solve it. You cannot just take 2 slices and just project it. Now again, doctors are trained for that. And again, we have billion years of evolution in this puppies. They simulate, like we virtualize. It's like, okay, the bones are looking like this. That's why generally doctor will ask for front and side view so they can visualize. Human brain is surprisingly good. So we can visualize, but you can't mathematically generate what exactly is going on here. It's like, hope for the best. And you must have seen that X-ray scan where they have to get what we call, your mouth has to be unwrapped. It's like, trrr, trrr. So we need many more slices to see. 2 slices is just not enough. Here, even in like Sudoku, if you have 9 slices, you can actually reach a point where you can constrain each number so much that it's like, no, only one solution will fit. The moment you reach that, ta-da, it's solved. So The slicing idea, good. Creating voxels, good. But you can't do with two. You need many, many, many more. And the more resolution you want, the more slices you have to do. So that's why basically we need multiple slices. So that's the mathematical part. Do not let anybody like convince you, oh, we can just like use AI and all that, blah, blah, blah. No, math does not. You have odd infinitum possibilities here. So we come to the part of tomography. Now let that be very clear. The reason why CT scan always has that C is that theoretically, on paper, this technology has been known from like 1930s. We knew how to do this. It's just that we could not do it physically. Without computers, this is like lol. So that's why the C part is always there, is compute. Without computers, this would not be possible. So same way, when you are looking at a generator, you can figure out how what is going on inside the generator. Heck, if you know what you're dealing with, you can actually tell, hey, what's the RPM of a generator? Even though all you are getting is the sinusoidal output on an oscilloscope. And you're like, they are related. That's how you figure it out. That's the whole point. Same thing can be done with X-rays and when you are scanning a human body, and it's a mathematical ratio. It will be there if you are using, let's just say, ultrasound. If you are using some sort of a microwave, it will be there. That's why the mathematics is tomography. Compute is the fact that we can now actually do it for human body. So voltage over time gives you the generator's rotor condition, like where is the rotor, which is it closer to north pole or south pole. If you just know the time and if you know the proper graphs of it, you can figure out a lot, almost everything. Now same thing can be done with slicing of your human body. Basically you take slice, and here slice means tuk angles, basically tuk. That's what we mean by slice. Not going like this, but going in 360 degree. Now that allows you to map the inside of human body. And again, inside of anything, we also do it for industrial stuff. So 360 would be classified as one slice. Basically, when you look into 3D printer, it has just one layer. So one slice is one layer, and that layer has data of 360 degree. Now, how many data points it will have in 360? Generally, one per degree, bare minimum. Like I do not even know any machines that go that low, but that would be bare minimum. Again, it's not necessary to go that low, that high as in 360 slices. It's just that it's recommended because again, human body is complex and you want to look at soft tissue. So higher the data points, the more clarity you're gonna get. So 360 degrees for one slice. Now, what is the output? You have the sensor, you have the X-ray, you have the sensor block. What will you get out of it when you are spinning it like crazy? It could spin as high as 300 RPMs. So that puppy is fast. So what do you get out of it? Like if you connect the data signal, what do you get? You get this puppy. Basically, you have an object, you have X-rays going through there, basically X-ray source going there, and you have a detector. So what is detector reading? Detector is reading this puppy, which we call sinogram. It's exactly like sinusoidal, sinogram. Now, again, I'm reasonably sure I do not have to explain, like this does not make sense. It's just a white squiggly lines. But somebody, very smart people, and if you ever wondered what the hell people do mathematics with, mathematics is like, oh, I can see a skull here. It's like, what the hell? Fourier transform and blah, 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 and filter back projection. Ta-da! You back project it. Basically, if you need, if you know the rotation, basically, where was the sensor? When like this slice is your the best way to describe would be luminosity, basically how bright this puppy was. So you black parts are super bright, X-ray just hit it, and then white parts are not, where X-ray was attenuated. So you have reduction. And then that's your one slice, basically the width of the sensor. Tada, that's one point. And this is moving along as you are rotating around. So you're getting sinusoid. To lock this axis, you need to know what was the rotation. Basically 10 degree, 20 degree, 30 degree, 40 degree, 50 degree, you need to know. And of course, it will go to 360. That would be completion of one slice. Now, once you want to have this data would be digital data. You feed it back into a computer and computer reconstructs it. Why? It just do the same thing. It does the same, but instead of absorbing data, it has the data, is projecting it and letting it intersect in voxel space. And ta-da! You can recreate the Of course, it does require some filtering. So it's called filter back projection and some extra filtering. You do need to do a lot of filtering in this, but you will get full construction of inside. That one slice is not just a 2D compression slice, it's full 3D. There is depth in this. So that way you can get full-fledged what's going on. And again, you will do multiple of these slices, basically that 360 slice, you do it in multiple, as in like thousands of them. And when, voila, you will have very high resolution 3D voxel data, what's the hell is going on inside the body. Plus, overlapping is desirable. Now, be mindful, mathematically, it's a very hard problem to solve how the heck you have overlapping, but it's a desirable, and we have much better computer now. So there is generally a lot of overlap, and benefit of that is you can just yeet the patient as quickly as possible. Because again, we are dealing with X-ray. You want the patient exposure time to be minuscule, negligible, should not be there. It should not be like MRI where they're like, oh, you are inside this tube which is screaming like a crazy man and it's very uncomfortable and you cannot move and everybody is screaming at you, please do not move. And they're like, yeah, stay there for 30 minutes. Not good. This is like yeet out. They can even make conveyor belts. So just put the patient there. They can do that. Oh, by the way, that is done for a lot of X-ray inspection equipment. So let's understand the X-ray part of it. So X-ray, you want a point source. You do not want a broad light source. Basically, no, you want like bright laser. You want a laser that is expanded. So all the beams are very known quantity. Basically, this cone should be a known quantity. It should not have like, the cone should have starting point. It should not be like this. So point source as pointy as possible. And again, X-ray is very harmful. So you want to make sure the exposure is very low as possible. Now, is it safe for people? Most people, yes, absolutely. And generally, people do not just go YOLO on CAT scans. Generally, you have an issue where if that issue is left untreated, you are in much bigger risk. For example, if I have let's say blood clot or a cancer, that if doctors cannot diagnose it reliably enough, this minor dose exposure to me is like, yeah, this may cause some issue 70 years down the line. You will not live 70 years if you do not have this treated. So they're like, go into this. And the only time they will have some reservation is generally pregnant women. For a pregnant woman point of view, they're like, yeah, generally the technician might stop the CT scan. It's like, if she's pregnant, she has to have a like good reason from doctors, not from her. From doctors, like why you need CT exactly. Generally, they will prefer her to shift to MRI. But again, then the problem is women have to be really good. And again, some people are really comfortable in MRI. I am not. I have no idea. Hats off to you if you can handle MRI 24/7, but I cannot. And they might have to use anesthesia. And again, that has another hassle. So X-ray is very harmful. Low exposure, that's the key. You want to do it as fast as possible. And again, that's another reason why we want to have overlapping data. So you do not, oh, we missed this data point. No. There is no missing the data point. Now, you have X-ray source, super easy. You just take ludicrously high voltage, you put it in a chamber, DC high voltage, and then you send electrons from one source, generally tungsten. You dump that puppy into a cathode, and that cathode is like yeet. The X-ray basically is emitted when electrons energy is trying to slow down way too quickly. So it has to dump energy somewhere. Sometimes it dumps it via photon, and that photon is so high energy is in X-ray band. So you get that X-ray generation there from X-ray tube. It's a basically vacuum tube technology. So you have vacuum tube that is glowing in X-ray, and then you have to basically filter this puppy. Now I have to say the best naming convention ever, bow tie filter. So there is a bow tie there. The idea is because again, it's a point source. This area will get very high exposure, so to say, as in like the intensity would be too damn high. So they want to make sure the intensity is kind of neutralized, so to say. So again, all of these things can be handled in computers. But again, you have to remember ancient technology, we did not have computers, and you do not want to have higher exposure. So bow tie filter is just allows them to neutralize the exposure here. Basically, it becomes more even. And then you have collimators, which is like big, thick metal blocks that are like, no X-ray will go from here to there. That's why you generally see lasers in those systems. The collimators are calibrated in such a way with those lasers that the person, if it is there, it's getting captured. You do not have to worry about it. And after that X-ray is emitted, gone through your body, now it has like, it was emitted with 100 oomph, now it went through your body, now it has 2D data, where it's like where I am and how much I lost. Basically, it came with 100 oomph, it only dumped like let's say 70 in your data sensor, you're like, okay, 30 was lost. That's how you create that scinograph and sinograph, sorry. And then how the heck you detect it? Well, you detect it via what we call scintillator. Scintillators are a fancy materials that can convert high energy photons into lower energy photons. Ancient technology of CFLs, you must be remembering that. CFLs used to have ultraviolet sources, meaning the glow inside the tube was ultraviolet. Then like how the hell we can see it? Well, the glow was high energy photons, ultraviolet high energy photons. Those were bumping into phosphors. Phosphors were like, chill down, bruh. And it was dumping all the energy. Basically, it's taking one high voltage photons and dumping into two lower voltage ones. It's like, hey, chill, ultraviolet, chill, blue light. So it was chilling it down. Same thing here. We take X-ray, we chill it down. And that's how you get your X-ray to light conversion, light to electrical signal conversion. We got this, we good. And sometimes people have figured out how to create a better technology where it's like direct conversion, X-ray into data, which we call cadmium-based systems. Basically, the sensor block can directly convert it. Basically, how we have silicon that converts photon into electrical signal, cadmium can do that with X-rays. Of course, not raw cadmium. It has certain alloys and blends and things of this nature. So that's how you actually get the digital data out of it. And then you have to understand, we have to utilize what you call anti-scatter grid, because again, that's a point source, still not 100% point source. Let's assume it is point source. When X-ray is going through things, X-rays do react with things, otherwise you will not get any data. It's not gamma rays. It does interact with things, and interaction can cause some weird effects, meaning it can cause Tokyo drifting. You want this cone to be perfectly perfect, but it could literally have a photon that is supposed to go from here, it can go twing. So what the hell? That happens generally because if X-ray photon hits the, so to say, electron cloud, it can change direction. It's like, it Tokyo drifts it. So that Tokyo drifting causes blooming. Basically, it's not good for your sensor. You will not get clean data. So how do we clean the data? Well, we create a wells, which we call scatter grids, so to say, anti-scatter grid. And these are very deep holes, like very deep, very thick metal, generally lead based. And the core idea is that X-ray, if coming from here, it has to be here. If it's coming from center, it has to be center. It cannot be like Tokyo drifting. No, there is no Tokyo drifting allowed in this. So it filters all that noise, so to say. It makes the data point much clearer. And then you have to understand one core aspect, the photon. Basically, you're like, wait a minute, aren't they huge? Yeah, they're huge. If you are coming from your mobile phone, you must have seen, like, we have made sensors so small that we can't make it any smaller because it will be smaller than the wavelength of light. We are that small, like we good. But when you're talking about here, the sensors are still measured in like, yeah, 0.5 millimeter. And that's a good sensor. Like Canon is screaming, it's like, we have achieved 0.5 real true resolution. I'm like, damn, like 70, 80 gold. So that's the whole point. It's the pixels are very big now. They're like, how can you get such a high resolution of inside of human body? Motion. That's why this puppy goes, and be mindful, that's one axis of motion, and you're just doing this also. You're two axising it. So you're getting a lot of data. And again, you also have a lot of overlap. So that allows another mathematical formulations to filter out the noise, crisp out the resolution. So that's the X-ray part of it. Now, the biggest question people will have when they see is like, how the heck it's carrying that sort of X-ray tube? Because X-ray tube requires high voltage, like bonkersly high voltage. Like we are talking about 40 kilovolts kind of high voltage. Not all of them are that high, but they can go. And some might say, oh, I have dealt with 100 kV one. They do require oomph. And not to mention, detection also need to dump data, lot of data, very quickly. So the technology was slip ring. Now again, ancient technology, we used to make them. And the core problem with this ring is that it requires a lot of power. Now, X-ray requiring high voltage, you're like, okay, why can't we just dump high voltage here? If you dump, it will cause short circuit. High voltage requires a very strong insulation. When you have something like this, there is no insulation, like from a high voltage point of view. So generally, these puppies are limited to low voltage of 1000 volts, and amps they do carry. They're big puppies. So these puppies can easily handle up to 300 amps. You can buy the brochures and you can figure it out. That's how I know. So you can download, sorry. You can buy also, but you can download also. And then slip ring are generally not used for data. I have no idea how the heck so many people keep saying that, oh, that's how they are dumping data. That used to be the case, like the very early, but that died long ago. So you have this, dumps the energy into the main rotor. Rotor has a very high voltage converter. Basically, it takes the low voltage of 1000 and makes it to 20 kV, 30 kV, whatever kV required, and then creates the X-ray. Then X-ray goes to the sensor block. Sensor blocks also consume some amount of power to do all the electronics and data gathering. After the data gathering, it has to transmit it back. And again, it's spinning. So how the heck it transmits it back? Again, there are certain way of dumping some low data throughput from this puppy, not recommended. So generally, it goes through either via optical fiber or it goes through capacitive coupling. Now, optical fiber, you have to understand, like, because it's a hollow tube, it's very difficult. So what they do is like they have a ring around that. So around that ring, there will have a emitter, so to say, that fiber optic emitter every few degrees. So it's like 10 degree, 10 degree, 10 degree, there are emitters. And on the receiving end, there are receivers that are multiple of them. So there is always overlap that transmits the data. Messy. Another aspect is capacitive coupling. If you remember your capacitors or electro boom, you know for a fact that capacitors stops DC but just YOLOs basically AC. Then you're like, okay, how the heck you have AC? It's air core capacitor. One side is spinning, one side is static. You've put basically AC signal into one side, it dumps into second side without any issue. So this sort of contactless transmission technology is used, and it can work at 5 Gbps. Like again, the ancient manual I found that had that. So I'm pretty sure the modern ones are very fast. Some of the latest optical one were claiming up to 20 Gbps. Again, we want to have lot of slices, lot of overlap data, and we want to spin that puppy like there is no tomorrow. So we do need bit of high bandwidth. So that's there. And sinograph does require one core vector. Where the hell was the X-ray source, or like what is the rotation? So encoders are also there. Basically, it tells the position. Without all these three things, the CT scan will not work. So you need some way to dump GG amounts of power, some way to extract GG amounts of data, some way to tell where the hell were you. Like, were you at 0 degree, were you at 10 degree, were you at 30 degree, where the hell were you? So that's the magic of slip ring, giant slip rings. So this was my presentation on basically CT technologies. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.